We're now going to dip our toe into special relativity. You actually have all the math and physics background you need to understand special relativity, but somehow it's still conceptually very difficult. I think this is because in most presentations, there's these very artificial examples of a train and lightning striking at both ends. Contrived situations are de rigueur. So I've really focused down and come up with a real world example that I think will help keep the discussion grounded. And now it's time for the hunter and the butterfly and the ant and the selfie stick. I will play the hunter and I'll be using my favorite gun. This is a Callahan full-bore autolock with customized trigger, double cartridge thorough gauge. I call it Vera. Vera will remain still, so she's going to stay in the lab frame. Let's measure Vera's muzzle velocity, since this is about relative frames of motion. Let's see, so I've marked out a couple of meters here, and 24 meters per second. So we also have a bullet frame, and the velocity of the bullet in the lab frame is 24 meters per second. So now I'm going to hunt butterflies. So looking around, and oh, there's one over there. Let's see if I come up with here. Okay, I'm lined up. Okay, Vera does not miss. Very rare that the butterfly escapes. But what happened is the ant. There is an ant on the bullet. He looks like this. And as a fellow member of the class Insecta, it's trying to help the butterfly. So the ant throws a rock at the velocity of 5 meters per second. And let's see, that would be the rock in the bullet frame, because the ant's riding on the bullet. So this is just like the Galilean transformations we already talked about. So let's look then and see, does it make sense that the rock got there first? Let's just look at the rock motion for a second here. Right, so what we want to know is what's the velocity of the rock in the lab frame. Right? So remember, whenever we want to do that, we say rock in lab is the velocity of the rock in something plus the velocity of that something in the lab frame. And the something, of course, is the bullet frame in this case. It's the rock in the bullet plus the velocity of the bullet in the lab. These are the Galilean transformations we were just doing. So in this case, we find that, let's see, rock and bullet is 5 meters per second, plus bullet in the lab frame we said was 24 meters per second. So sure enough, as your intuition would tell you, since the rock was thrown at 5 meters per second from a moving bullet at 24, the moment it was thrown, it's going at 29. It's going at 29, the bullet's going at 24, so of course the rock got there first, and that's what warned the butterfly, and that's the only reason I missed. But what if the ant doesn't have a rock? Well, the ant still wants to protect the butterfly, so the ant would shout, "Look out!" Right. And that's, of course, sound. The ant would send a sound wave towards the butterfly. So to figure out how this will work in terms of frames of reference, let's talk a little bit about sound. Sound is a wave. So we have to think a little bit about waves. You could take my class, Physics 201X, here on edX, Waves and Optics, highly recommended. Or you could just listen to what I'm going to tell you. So waves are the propagation of energy through a medium. The energy is carried through some disturbance. So in the case of sound, the disturbance is a little bit of a variation in pressure. A little bit of a pressure wave moves through the air and goes, in this case, from the ant to the butterfly. And the other thing, what we really care about, is waves move at constant speed with respect to the medium. Each wave is a different kind of disturbance, and each wave has its own unique medium. So, as I said, sound is a pressure wave in the air. So it moves at a constant speed in the air. This velocity of sound in air is about velocity of sound in the frame of the air, about 340 meters per second. All right. So now let's think about the relative scenario. Let's look at the sound motion. Okay. And I'm putting motion in quotes because, again, sound isn't a physical object like the rock, but we can still think about how fast it's going to move. So first, let's ask ourselves, if the sound goes at 340, how fast is it really going in the lab frame, right? So what's the velocity of sound in the lab frame? Well, our rule for the transformations is you just write velocity of sound in something plus the velocity of something in what you want. Okay? So in this case, we have the sound in the air. So the sound in the air frame plus the velocity of the air in the lab frame. Okay? So in the lab frame, the sound is going at 340 plus, what's the velocity in the air frame? Well, we're indoors and there's no wind, so it's 0. Right? The air is sitting still. There's a little currents here and there, but the air is basically sitting still, so it's basically 0 meters per second. So the sound does go at 340 meters per second. So you can imagine if the bullet is going 24 and the sound is going at 340, then of course the sound gets there first, scares away the butterfly, and we miss yet again. An interesting question, though, is what is the velocity of the sound in the bullet frame, which is the same as the ant? How does the ant see this sound move forward or backwards? Let's see. Well, we follow our rule. We want the velocity of the sound in the lab frame plus the velocity of the lab in the bullet frame. Okay. Let's see. The velocity of the sound in the lab frame we decided was 340 because the air and the lab are the same thing. Okay. What's the velocity of the lab in the bullet frame? Well, bullet in the lab frame is 24 meters per second. We define 24 as positive this way. But you really got to imagine you're in the bullet frame. What do you see? You see the lab moving back. So you actually subtract 24 meters per second. It's negative 24 meters per second. So we get, what do we get? 316 meters per second. So even though we think of sound as going at 340, this ant, since it's moving, and since the sound moves with respect to the air, it actually sees the sound go a little bit slower in this direction. Might see it faster in that direction, but slower this way. So that's what the ant would do if it didn't have a rock. What if the ant had laryngitis? It still wants to protect the butterfly. So in this case, it holds up a strobe lamp. And the strobe lamp sends light towards the butterfly. That way the butterfly will see the light, fly away, won't get shot. So now we have to think about light. So light is also a wave of the EM field, the electromagnetic field. It moves very fast. Based on the properties of EM fields, we can calculate the speed of light, and it's 300 million meters per second. What we sometimes just call C in physics. It has its own symbol. Very fast, 300 million meters per second. But it's a little bit different because the EM field isn't really a physical material or object like air or like water, like waves in water. So it's really hard to define, think of it as being in a certain frame of reference. So in the late 19th century, people were really wondering what is the material that light propagates through? And they thought, well, it must be sitting with rest with respect to something, so surely we can eventually detect this thing. So they called it the luminiferous ether, as it was called. So how can we detect this ether and figure out, is it stationary with the Earth, or is it moving with the sun, or is it stationary with a galaxy? How does it work? So to detect it, the most famous experiment was by Michelson and Morley, or maybe it's Michelson and Morley. I don't know. I call it the M&M experiment because I don't want to say it wrong. And M&M detected it by a method called interferometry. And here is just the absolute basics of interferometry. If I shine some light at a mirror, it'll reflect back. And when it reflects back and overlaps with itself, it might be in a condition where the waves add and you get positive interference, or you get twice as big of a wave, or it might be a condition where they cancel and you get zero. So by whether they're adding or subtracting, you can detect very small changes. You can detect little changes in the spacing, you can detect little changes in the wave properties. It's an extremely sensitive technique. If you heard about the detection of gravitational waves in 2016, it was done by interferometry, extremely sensitive interferometry. So M&M set up an interferometer, and the idea was that we know that the Earth is moving through space pretty fast, right? So if this is the sun, the Earth is going at about 3 times 10 to the 4 meters per second. So if you imagine that the luminiferous ether is in space and it's at a constant velocity in space, maybe stationary with respect to the sun, maybe flowing this way, doesn't really matter. If I take my interferometer and hold it one direction relative to whichever way we're moving, I should see one set of conditions, and if I turn it 90 degrees, I should see a different set of conditions. Just by turning the interferometer, I can change how or what direction this light is moving with respect to however the ether is moving. So you don't have to know the details of the ether, just you had to set that up and turn it 90 degrees. So M&M did that, turned it 90 degrees, and saw absolutely nothing. They had a pretty good idea what they should see, because they know the speed of light, and they knew the speed of the Earth, presuming we're moving through an ether, but they got no results at all, which implies that there is no ether, which implies that there is no special frame through which light must travel 300 million meters per second. This really confused everyone, except Einstein. So Einstein had the insight to say, maybe Galilean transformations are wrong. Maybe it's actually the case that light goes this fast in any frame. So maybe it's the case that if we're standing here in the lab frame and we see the light come out of the strobe lamp, we say it went at 300 million meters per second. And if you're the ant on the bullet and he watches the light move forward, he also says it went 300 million meters per second. It sounds crazy to us because we grew up in a Galilean frame where this kind of effect isn't observed. But in reality, it's been tested to death, and this is really true. This is the basis of special relativity, the fact that light always travels at 300 million meters per second, no matter what frame you're in. This leads to a lot of weird stuff, and we're just going to look at one aspect of what it leads to in the next video. We're going to look at time dilation. One more thing, though, I want to tell you about the M&M experiment is that if you go online, you can find lots of very fancy videos about it with beautiful graphics, and lens flares, and soaring music, and very earnest people talking about it and everything. But they really miss the most exciting part of this paper. What often helps is to really read the paper. And here's my favorite part. In the first experiment, one of the principal difficulties encountered was that of revolving the apparatus without producing distortion. Remember, they had to turn it 90 degrees. And another was the extreme sensitiveness to vibration. This was so great that it was impossible to see the interference fringes except at brief intervals when working in the city, even at 2 o'clock in the morning. Scientists love to brag about how late they work, and they actually put it in their paper. Finally, as before remarked, the quantity to be observed, namely a displacement of something less than a 20th of the distance between the interference fringes, may have been too small to be detected when masked by experimental errors. So they're basically saying, this is really hard. They like to point out how difficult this is. But this is the part I love. As an experimentalist, I love this part. The first named difficulties were entirely overcome by mounting the apparatus on a massive stone floating on mercury. So they didn't have air tables back then. They had this thing mounted on this massive, heavy stone table, and they said, we need it to be supported. They said, screw it. Let's just put it on mercury. Go buy 50 gallons of mercury and float it. This kind of experiment could only be done by 2 people. Because if I were in my lab and I thought, I could float this on a big vat of mercury, I'd then think, oh, no, it's a crazy idea. But if it's 2 people, one person says, we could float it on a big vat of mercury, and the other person says, yes, let's do that, right? That's the reason only 2 people, or it required 2 people to do this experiment. It's the greatest thing I ever heard. If I tried to order enough mercury to float a table today, the FBI would be showing up at my door pretty quickly. The other thing, if you read this paper carefully, is something that often happens in science is we later sort of talk about how, oh, that paper made it clear at the time, and everybody understood as soon as that paper was published. That's kind of how we sort of remember things, often not how it is. So now we say, well, this was the paper that proved that there's no luminiferous ether. Well, that was not their conclusion, right? So at the time, they did not know they were proving there was no luminiferous ether. Their only conclusion really is that we are not moving with respect to a luminiferous ether. And if you read, they conclude that, and then they talk about how this impacts other people's work, and then they have a supplement where they say, here's some other experiments we could do to try to detect the luminiferous ether. So the conclusion is, one possibility is that it's more like a fluid, and as the Earth moves, it drags the ether with it, right? So right at the surface of the Earth where we are, the ether isn't moving, but out in space, we're moving with respect to it. So they actually suggest what we got to do is get one of these tablets and go up on a mountain and do this on a mountain really high where maybe the ether is still moving past the Earth. And they also say if we're doing this, we need to not have it inside a room because there were ideas that since light can't go through opaque objects like walls, maybe the ether can't go through an opaque object like a wall. So they say what you got to do is get this on a mountain and have like a glass covering over it so that the ether could freely move through. So they clearly had not dropped the chalk and said there's no ether. They were clearly still thinking about ether. But when we look back now, and then later when we discover the electromagnetic field, then everything makes sense, except the reference frame part that required Einstein to figure out.